Well, welcome to QOD 39 in Chapter 16 on acids and bases. Recording from the home studio today. The power went out at school, and so rather than wait for it to come back on, I ran home to um, record this. So, so far in this chapter, I think I'll confess I pushed pretty hard at the beginning of this chapter on the first few sections. And so what I want to do with this video is just introduce one more topic, and then we might be able to just ease off a little bit and spend some time in class working on things that we've learned. And so what I wanted to do is just sort of give an inventory of what we've talked about so far in chapter 16. The first thing was defining acids and bases, both Bronsted and Arrhenius. Um, we defined Kw, the ion product constant for water, the P function, and pH. We talked about conjugate acids and bases, the relationship between them, how to identify conjugate acids and bases, and then their relative strengths. That is, as strength of on one side goes up, strength goes down on the other side, etc. We've talked about pH and the relative concentrations of hydronium and hydroxide in either acidic or basic solutions. So an acidic solution has a higher concentration of H plus or hydronium. The basic solution has a higher concentration of hydroxide. We've done the exercise in class of calculating around the square, and probably the most practical application for that is calculating a pH in a situation where you know the hydroxide concentration of the solution. So that requires two steps. We've talked about the Ka expression, which could be expressed either in either of the ways that I've described here, either showing hydronium as hydronium or abbreviating it as H plus. And then we've just talked briefly about the Kb expression, which could appear in either one of these two forms. But if you just understand what the nature of the Kb expression is, and we'll talk about that a little bit more in just a second. And then we've done some practical applications of this in the video and also in class, calculating final concentrations, and therefore I'm sorry, I've got this backwards. Calculating Ka given initial concentrations and one final concentration. And therefore from there percent ionization. And so now we're going to do the thing that I've actually mentioned here, which I say wrong. So I'll back up. What we've done so far is calculated Ka if we know the initial concentrations and one final concentration, or the pH. We've talked about percent ionization. And so the last thing to do here, and the subject of this video, is to calculate final concentrations and therefore the pH if we know initial concentrations, and Ka if it's an acid ionization reaction, Kb if it's a base ionization reaction. So hopefully this is going to be fairly short. I'll just go through how to do this, and then we'll spend some time in class working on it. But what would a typical problem like that look like? Well, here's a typical problem. Calculate the pH of a solution of acetic acid that is 0.3 molar. So I take acetic acid, pure acetic acid. I take 0.3 moles of it, dissolve it up to 1 liter with water. So I've got a 0.3 molar solution of acetic acid. What is the pH of that at equilibrium? And so I've got the equilibrium reaction here. Acetic acid is going to protonate water to a small extent to give me hydronium ions plus acetate ions. And I can look in Appendix D of my book, which you'll get used to looking in fairly soon, and see that the Ka for acetic acid is 1.8 times 10 to the minus 5. Well, the one thing to do is remember that we know the equilibrium constant expression, and that is that Ka is equal to hydronium times acetate over acetic acid, H plus times A minus over HA. We know the initial concentration of the acetic acid, it's 0.3 molar. And so we can populate an ice table with that. Here's the equation. Remember, because the water is not a participant in the equilibrium constant expression, we also leave it out of the ice table. So the initial concentration of acetic acid is 0.3 molar. And then the initial concentrations of hydronium and acetate are going to be 0, but it's immediately going to ionize and equilibrate. Because Q is equal to 0 initially, the reaction is going to go forward. Therefore, reactant concentrations are going to go down, product concentrations are going to go up. The coefficient in each case is 1, so I can simply say that the change in acetic acid is going to be negative X. The change in hydronium and acetate is going to be positive X. At equilibrium, the concentration of both hydronium and acetate is going to be X. The concentration of acetic acid is going to be 0.3 minus X. I'm going to make a very important approximation here, which will help us avoid a quadratic equation. And that is simply to say that 0.3, we're expecting X to be a small number because K is a small number. So we're expecting X to be a small number. Therefore, we can make the assumption that 0.3 minus X is essentially going to be equal to 0.3. And that lets us avoid a quadratic equation and therefore having to apply the quadratic formula. So we're going to assume that X is going to be very small compared to 0.3, and therefore we can ignore it and just basically approximate that 0.3 minus X is equal to 0.3. But once again, we have this Ka expression for this specific reaction. And so I'm going to just plug in the values from the previous slide that I had into the Ka expression. Ka was, if you'll recall, was 1.8 times 10 to the minus 5. Both hydronium and acetate were X, and so I simply am going to plug in X for each of those, which is X squared. And we gave the initial value of the concentration, the value of the initial concentration of acetic acid as being 0.3. I can now take that and multiply both sides by 0.3. So 1.8 times 10 to the minus 5th times 0.3 is equal to X squared. Therefore, 5.4 times 10 to the minus 6 is equal to X squared. And therefore, X is equal to 2.3 times 10 to the minus 3rd. That is both my hydronium concentration at equilibrium and my acetate concentration at equilibrium. Because the problem was asking me for pH, I'm going to go ahead and say, okay, pH is the negative log of hydronium concentration. We just got through calculating the hydronium concentration as being 2.3 times 10 to the minus 3. The negative log of 2.3 times 10 to the minus 3 is 2.64. So if we have initial acid, the initial concentration of whatever our weak acid is, in that case it was acetic acid, and we know the value of Ka, we can calculate the equilibrium concentrations of everything and therefore use that to calculate pH. Well, we can also do this for a weak base. And so the sort of poster child for weak bases is ammonia. So if I want to ask the question, what is the pH of a 0.15 molar solution of ammonia? I'm essentially going to solve it in the same way. Here is my base ionization reaction. Ammonia is going to react with water to give me ammonium hydroxide. The K for this reaction is small. Coincidentally, Kb for ammonia is the same as Ka for acetic acid, 1.8 times 10 to the minus 5. That's totally coincidental, but it is a happy coincidence because you can teach a lot of acid-base equilibria just by memorizing one number. And so I write the Kb expression, its products, ammonium times hydroxide over reactants, ammonia. We don't include water because this is occurring in aqueous solution. And so therefore I can take that and set up an ice table. And what was given to me here is that the initial concentration of the ammonia is 0.15 molar. I'm making a 0.15 molar solution of ammonia. The initial concentration of the products is 0, so Q is equal to 0. Therefore, the reaction is going to go forward. All of the coefficients are 1. And so the change in the ammonia concentration is going to be negative X. The change in the ammonium and hydroxide concentrations are going to be positive X. Therefore, at equilibrium, the concentration of both ammonium and hydroxide, each of those is going to be X. And we're going to make that same assumption that X being so small, because again, K is 1.8 times 10 to the minus fifth. So we're expecting X to be so small that it's insignificant compared to 0.15. And therefore, we can make the approximation that 0.15 minus X is essentially equal to 0.15. This again is significant because it allows us to avoid a quadratic equation. Okay, well, we said that Kb is equal to the ammonium concentration times the hydroxide concentration divided by the ammonia concentration, and is equal to 1.8 times 10 to the minus 5. So I'm just going to substitute these values into that Kb expression. Both the ammonium and the hydroxide were X, and so the numerator becomes X squared. The denominator was, for all intents and purposes, 0.15, so I'm going to put that in. And I set that equal to Kb. Multiply both sides by 0.5 so that I've got my X term on one side and all my numeric terms on the other. 2.7 times 10 to the minus 6 is equal to X squared. Taking the square root of both sides, I get the 1.6 times 10 to the minus 3 is equal to X. Now I need to determine the pH from that. Remember, this X is equal to the hydroxide concentration. So I'm going to have to go around two sides of the square to get from this hydroxide concentration to a pH. We've done this both ways in class. The way that this set of slides does it, that I'm just going to slavishly follow, is that they're going to convert a hydroxide concentration into a POH. And so the POH is the negative log of the hydroxide concentration, which is equal to 2.80. Now, to do the other leg of the square, if you're going in that direction, you're simply going to remember that POH plus pH for any solution is equal to 14. Therefore, I'm going to take 14 minus 2.8, and that gives me a pH of 11.2. If I did the opposite thing, which was to take this this hydroxide concentration and use Kw to convert it into an H plus concentration, and then take the negative log of that H plus concentration, I would still get 11 point. Well, I think that's the end. You guys should all be rejoicing that this is a 13-minute video. And so what's the QOD going to be about? Well, some of it, I think, is going to be offering a second chance for some of the perhaps slightly unpreparedness of the previous QOD. And so there'll probably be at least one problem on this QOD similar to the ones that were on QOD number 38, and then something else related to this that I'm sure that I can dream up. So thanks for watching. Please try some of the suggested practice problems before class. Thanks.